Very important session because it's before our Right, so and our first speaker, Nikos Pavlidis from Lancaster University, who's going to talk about high-dimensional incremental divisible clustering under population.
All right, thank you. So let me start by thanking the organizers for inviting me here, and let me also point out that this is joint work with myself, David Hofmeyer, and Idris Şekli, who are all from Lancaster University. So the subject of the talk today is going to be on how to perform clustering when we are observing data sequentially and potentially in a very high frequency from a population distribution that is subject to change. Okay, and we need to do that for high-dimensional data and in an online manner. So before I introduce the full problem, let me just say a few words about what is clustering. Clustering is one of the most central problems in statistical pattern recognition and data mining. And one way to define this problem is to say that clustering is the process of partitioning a set of data into groups or clusters so that observations within each group are more similar to each other than observations that are allocated to different groups. Clustering has been applied in a very wide number of applications that include astronomy, physics, medicine, biology, psychology, marketing, and so on. And there are two goals that one can associate with performing clustering. In the first case, we might aim to improve our understanding about the data set that we have, and we do that by identifying some sort of natural groups that are present. Or in the second case, we might be performing clustering as a first step towards a different purpose. So we might want to perform data compression, indexing, or even modeling and forecasting after these natural groups have been identified. Now, a problem that we have in clustering, which is not the case in classification, is that in clustering we never really observe the true label of the different observations. So we don't know to which class the different objects actually belong. The consequence of this is that there is no unique definition of what is a true cluster or a true group. And at the end of the day, when we are applying this in practice, we need to rely on the characteristics of the specific application to define what does it mean to be similar in this application, and therefore what does it mean to belong in the same group. Now, clustering has a very long and rich history for the last 50 years at the very least. However, in the last decade, we have a very large number of new methods being proposed and analyzed in the literature. And the reason for this spike in the interest in the field is that we have a large number of new challenges that arise from progress in data generation and acquisition technology. And these technologies are being used in a constantly increasing range of applications. So such examples, for instance, include clickstream data, web blogs, emails. And our aim is to analyze such problems. Now, as I mentioned before, the aim of this work is to develop a clustering framework for the cases when the population distribution is in high dimensions. It could be potentially subject to change, and the data is observed sequentially and at a high frequency. It is important to stress that each of these problems have been investigated in the clustering literature to a different extent each problem. Some problems have been very well investigated, like the problem of high dimensionality, where problems like time variation have been less well investigated. However, to the best of our knowledge, very little work has been done in investigating all three aspects at the same time, and very little consideration has been paid on these methods that have been developed over the last decade of how can you extend a method, for instance, for high-dimensional data to deal with different properties such as sequential observation of the data or population drift. So the novelty of what we propose lies in considering all of these aspects at the same time. So let me just motivate why these are challenging aspects for clustering and why this is something that has attracted a lot of research interest in the last decade. The first and perhaps the most fundamental problem for clustering among the ones that I'm discussing here is the problem of high dimensionality. And this is such a fundamental limitation because a number of results, starting by the famous result in Bayer in 1999, state that the relative distances of a random point to its furthest and nearest neighbor tends to 0 as the dimensionality goes to infinity. So when we are looking at very high dimensional data, our usual notions of similarity, which rely to some extent on some notion of distance, like the Euclidean distance, become less and less meaningful. And people tend to say that distances between points become relatively uniform when the dimensionality increases. So this is a fundamental limitation for clustering very high dimensional data. However, that does not mean that there is nothing that we can do to address applications that involve such data sets. And the reason for that is that very frequently we are able to perform some sort of dimensionality reduction method and reduce the problem to a lower dimensional space, in which case we can use distances and we can enjoy the nice properties that we had before. There is, however, a limitation to this approach, and the limitation is that when we are looking at high dimensional data, the approach of just pre-processing the data and then applying a clustering algorithm on it is not ideal. And the reason for that is that different clusters can exist in different subspaces, and different correlations between different sets of features can be important for different clusters. So instead of applying a global dimensionality approach and then clustering, what we are really trying to understand is to understand the local feature relevance, a local feature correlation problem. So we want to identify features that are important for each cluster and correlations that are important for each cluster separately than for all the data together. So if we want to look at the high dimensional clustering problem, one can say that it can be decomposed in two sub-problems that need to be solved simultaneously. The first one is the search for the relevant subspace. Okay, so in which subspace should I perform dimensionality reduction? And the second problem is how, after I have done that, how to identify the final set of clusters. Okay? And we need to do that simultaneously. Both problems are extremely challenging. The first problem has, in the general case, a search space that is potentially infinite. The second problem has been shown to be, in its most general form, NP complete. So the algorithms that we have for high dimensional clustering effectively combine heuristics to attempt to solve these two tasks at the same time. And most of these heuristics involve some sort of dimensionality reduction using linear techniques like principal component analysis or support or SVD. This has been a very active research area over the last 10 to 15 years, mainly motivated by the large number of applications that involve this type of data. However, for our purposes, very, very few, if any, of these methods that have been developed can be applied in a sequential manner. Okay, so all of these methods assume that you have access to all of the data and you process the data iteratively many times in order to come up with a final result. I got it. All right. The second aspect that we need to consider is the sequential character of data observations. And this is a paradigm which has been known in the last years as the data streaming paradigm. So we can define a data stream as any process that generates data sequentially and at a very high frequency relative to the available storage and computing requirements. So this is another form of doing an online problem where we emphasize effectively real-time processing of the data and being able to update the model in real time. And another requirement that some authors include in the definition of data streams, some authors don't, we do in this case, is that the data generation process from this phenomenon can be liable to unpredictable change. So there could be different types of change, abrupt change, gradual change. In principle, we know very little about this, and we are trying to develop an adaptive model to accommodate all of these different factors. So if I can just summarize the requirements.
The microphone is...
No?
Go.
Oh, sorry.
Yeah.
Okay. All right. Thank you. So when we are looking at streaming data, we have a set of requirements. First of all, any algorithm for streaming data must be able to process a single example as it arrives. We do not assume that we have any control over the order in which examples are observed. Once inspected or once processed or ignored, this example has to be discarded. Of course, we make an allowance that you could have a small working memory. Okay. Secondly, the update of the model has to be performed using limited memory. right? So typically we assume that the size of the data stream is much, much larger than the size of the working memory. So approaches which rely on storing everything and iterating over it multiple times are not feasible. And basically any algorithm that has storage requirements proportional in some way to the size of the stream will eventually run out of memory. Due to the high frequency characteristic, we also want any algorithm to be able to process observations in a limited time so as to be able to make decisions in real time or as close to real time as possible. And the final requirement is that we want the algorithm to be anytime, and that basically means that at any point in time we want the algorithm to be able to produce the best possible model given the data that it has observed and be able to use that model in order to make predictions. Okay. So algorithms that instead of actually storing a model, store some sort of summary statistics and then re-estimate the model based on those summary statistics and so on, are considered to be relatively inefficient in this sort of framework. Okay. All right. So let me summarize what I believe to be the methods for high-dimensional clustering of data streams. As you see, this is a relatively short list. If we had a list of methods for high-dimensional data, it would be extremely much longer. The first algorithms for streaming data just assumed that mining or clustering data streams is a variation of the one-pass clustering algorithm, and there are many, many algorithms to do that. However, when the population distribution is changing over time, if you apply this kind of algorithms, the result that you can get can be very, very misleading because changes in the location or the number of clusters will be averaged out throughout the run of the algorithm. A simple alternative is to use a sliding window, okay, where you use a predefined number of previous observations. This is the critical parameter for the success of this type of methods. So at each time step or whenever you want to evaluate the clustering result, you execute the clustering algorithm of your choice. It could be a clustering algorithm for high-dimensional data on this window of previous observations. Now, this is a very widely used approach, especially in classification. For clustering, there are serious problems with this approach. The main problem is that the clustering result can be very unstable and inconsistent. So we could have observations being allocated to different clusters, different numbers of clusters, and so on, and all of these things in consecutive time steps. Okay. There have been some work on trying to alleviate this problem using appropriate penalties, but I will not talk about these methods as they are more suitable for a different type of problem than the one that I am considering here. The most influential type of method for streaming data is an algorithm known as clustream, proposed by Agarwal in 2003. Basically what this algorithm is doing is it relies on the concept of a microcluster. So instead of using the raw data, we define a microcluster, which is a structure that accumulates information about the first and second moment of the location information, and also the first and second moment of temporal information. Okay? So this, if you want to visualize this, effectively instead of looking at the raw data, we are looking at spheres, and the radius of these spheres depends on the variance of points that fell into that object, and the mean represents the central location. So what this algorithm is doing is instead of clustering the raw observations, which we cannot store, it clusters these microclusters at every time point. Okay? So we can use an offline algorithm on these microclusters rather than the original data in order to get the clustering result. Now, this, as I just described before, is not efficient from a streaming point of view because you have to run this offline algorithm every time point. Another very important problem of this algorithm is that it utilizes a really very large number of parameters, some of them having very little, if any, intuitive meaning. Okay? So you need to determine parameters, you need to set parameters such as when should a new microcluster be initialized, when should different microclusters be merged, which observation is considered as noise, and all of these things are determined by user-specified parameters, which you set at the very beginning. Non-stationarity in this context is handled effectively using windows, so this algorithm is storing at consecutive time points snapshots of these microclusters at different granularity. So you save at the current point, 2 points, 4 points, and so on. so if you want to identify the clusters in the last, let's say, 1,000 time steps, because of the additive property of the mean and the variance, you effectively remove the impact of observations before that time point, and you look at the clusters just for the last 1,000 time steps. So this doesn't really solve the problem of name stationarity. It asks the user to specify the right parameter to do that. An alternative approach offered by the same author in order to handle high dimensionality directly is what is known as the HP stream algorithm. So it is effectively a high dimensional version of class stream. The main difference here is that each microcluster here now is a cluster. So each sphere that you accumulate information about is not just a component, but it's rather a cluster in its own right. And in order to take into account the impact of time, you are using a fading function or forgetting factors, so you are imposing an exponentially decaying schedule on the contribution of each observation, where the user has to specify what this schedule will look like. Okay, and finally, both algorithms require an offline initialization step, so they cannot be run directly. Okay. So let me just now describe the motivation for our approach. So our approach is based on what is known as projective divisive clustering. This is a process that is designed for very high dimensional data set, and it effectively decomposes the clustering problem into 3 very simple steps. The first is to identify a projection subspace. The second is to evaluate whether in that projection subspace the sample, or what you consider the cluster, is separable or not. So are there 2 or more clusters in that subspace? And if that is the case, then you need to specify a criterion to separate the different clusters, whether that is in 2, 3, or any number of clusters. The most influential work on this field is known as the principal direction divisive partitioning algorithm. It was proposed in 1998, and this algorithm effectively makes the simplest possible choice to solve each of these subproblems. So the way that this algorithm works, we use a one-dimensional projection subspace, so we project everything onto the first principal component. Okay? This is the direction of maximum variability, and the algorithm assumes, although there is no guarantee, that the clusters will be separable in that direction. And then as a splitting point, this algorithm imposes that we're going to split at the mean of this projection. So if your data is centered at 0, that basically means that you are splitting at the point of 0. So anything greater or smaller than the mean. Okay. And to evaluate which cluster so you separate into 2 clusters. This creates a binary tree, and every time you measure the scatter value, a measure of variability within each cluster, to define which sample will be further subdivided, and the algorithm terminates when you find the desired number of clusters. Okay. So in order to do that, you require some domain-specific knowledge. Now, a variation of this algorithm is known as the density-enhanced version of this. The main difference here, again, you project on the first principal component. The main difference is instead of splitting at the mean, the authors are trying to avoid splitting individual clusters. So what do? They perform a kernel density estimation of the density, of the marginal density on this projection direction, and they split at the global minimizer of this density. Right? So, and the intuition behind that is that you are hoping that if you split at this minimizer, you are going to avoid introducing a hyperplane that will pass through dense regions of the original full dimensional space. So in that sense, you are going to avoid splitting this middle cluster here, and obviously in this artificial example, you succeed. Okay. Another nice property of this method, however, is that it can give you a data-driven criterion of when to terminate the algorithm, and in particular, when on every first principal component that you have, the distribution is unimodal, then you can claim that you have identified the right number of clusters, and you can stop. So this is going to be our starting point for what we are going to discuss. And let me explain why. First of all, these algorithms are suitable for high-dimensional data, so we could decompose this very difficult problem into a collection of simple subproblems. This approach also exploits sparsity, so although the final clusters are going to be effectively convex polyhedra, if your data is sparse in the high-dimensional space, this limitation, we hope, is not going to be too problematic for recovering the real clusters. So from an incremental point of view, we also have some basic tools that we can use for this type of problem. So there are incremental PCA algorithms that have a guaranteed convergence, okay, and they require a constant time and memory complexity. Okay, so you don't have to resort to methods like gradient descent. And also there's been a lot of work recently in incremental and adaptive kernel density estimation. Okay, so we hope that if we combine methods from these two fields, we could have a first running version. Now, these are the advantages. On the other hand, we have a number of difficulties on trying to present this for the streaming case. First of all, it is not clear when we should separate a cluster. In the static case, this is obvious. You look at the unimodality or not of the distribution. But when you observe observations sequentially, you have no way of knowing what will happen in the future. Also, we have the problem that if we continually update this model, like, for instance, moving around the microclusters, then this is going to result into, this instability is going to compound into the binary tree that will represent the final clustering result. Okay? So we need some sort of way to make this more stable. And lastly, in everything that I have discussed so far, we haven't dealt at all with the issue of non-stationarity. So I will try to describe the steps that we use in order to solve each of these problems. The most established, at least to my knowledge, test in order to assess a unimodality of an empirical distribution is the deep test, which is proposed by Hartigan, who did a lot of influential work on clustering as well. And basically, this test for the multimodality of a one-dimensional sample by finding the closest empirical distribution to the current one that is unimodal, and then comparing the empirical CDF to that of the sample using the supreme norm. Okay? And you can get confidence bounds using Monte Carlo. The problem with that is that in order to do this deep test, you require the full sample. Okay? So you need to store all of the observations, which is something that we want to avoid. So we have developed an approximate way to do that. The approach that we have effectively relies on defining M compact intervals, where M is a user-defined parameter. You can set it according to the available memory. And then for each interval, we basically count the number of observations that fall within it. Okay? And there is a simple way of expanding or decreasing this range so that it covers the entire range of observations that you have. And we have shown a lemma that says basically if you approximate the deep test statistic using this finite sample, you obtain a lower bound as compared to the deep test statistics that you would get if you had the entire sample, which is positive for what we want to do, because what we are trying to avoid is to avoid introducing erroneous splits, so splitting the data in clusters that do not exist. Another nice property of this, of course, is that the user can specify the certainty with which a certain decision is required. So in my view, this is a more intuitive way of defining when to split. So once we identify that the distribution on a particular projection direction is multimodal, we decide to split this cluster, and once this decision is made, we fix the projection direction and the splitting point. And this is done in order to avoid instability going down the leaves of the tree. The second problem that we have is that for any incremental PCA algorithm, the projection direction is going to be changing over time. Okay? So if you are every time projecting a single point on a moving projection direction, and of course you don't store the point, the original point, but rather the length on this vector that you have, because this projection vector is shifting, effectively you end up having a sample from a non-stationary distribution, even if the distribution of the population is static. Okay? So we need some way of countering this, and the popular way to do that is to use some sort of forgetting factors, which are defined as a parameter lambda between 0 and 1, and then the weight of each point in the kernel density estimator is exponentially decreasing based on how far away, how far in the past it was observed. Okay? And this is a general form of writing the kernel density estimation with a forgetting factor. The problem that these methods have, they are widely used in the adaptive filtering literature, is that it is practically difficult to tune this parameter lambda, which is crucial for the accuracy of your sample. So we have been able to show that if you use information from the angles between consecutive projection updates. So this is what the arc cos of the inner product. This is the projection direction at time t plus 1 and t. And your projection direction converges in probability to a constant projection direction, which is guaranteed by this incremental PCA algorithm as long as the population distribution is static. Then this very simple scheme is going to make the forgetting factor go to 0, and that effectively means that you are not discounting data anymore. So we have this lemma that if the projection direction eventually stabilizes, the accuracy of your kernel density estimation will start increasing, okay? And the down weighting of previous information will depend on how fast it was moving in the past. I think this slide is the most interesting from this workshop. Everything that I have said so far only deals with the concept of doing clustering incrementally. We have not discussed at all about any sort of change. And in the general clustering problem, we have a very large number of potential changes that can happen. Okay, so we can have new clusters being generated, old clusters disappearing. We can have clusters moving abruptly or gradually, changing shape, and so on. So we don't want to deal with this problem in its full complexity in the high-dimensional space. And the intuition behind the proposed approach is that we are interested effectively in identifying changes that make part of our model irrelevant, all right, or wrong. And these changes are changes in the clusters that will invalidate a splitting point. Okay? So if in this two-dimensional example, the gray are the clusters before and the black ones are the new clusters. So in this case, we have a shift of this cluster, all right, and this invalidates this splitting hyperplane because it intersects the cluster, so we would need to revise this model. But this change, this shift here, has no impact on our model, so there is no reason why we should discard this separating hyperplane and start building a new model from there. Surprisingly, this is true for all sorts of different changes. So this is a change in the shape, so this cluster is shrunk, this is expanded. This is not a problem. This part of the hierarchy needs to be revised. And even the creation of new clusters can be accommodated along those lines. Okay? So if a new cluster is created in a leaf node, we don't need to revise any part of the hierarchy. We can just further split there. Otherwise, we need to revise some part of it. Okay? So this is nice. And another nice property of this approach is that unlike change detection methods in streaming data, when you identify a change here, you can localize the part of the model that needs revision rather than throwing out everything and building everything from the beginning. Okay? So not all change renders the model obsolete. So how do we define that? We propose a very simple approach. What we are interested effectively is testing the hypothesis that the split point remains a local minimum. So if this is a kernel density estimation, these are the two adjusted modes relative to the local minimizer that we have selected as the split point. We define two neighborhoods. The larger neighborhood goes from the one mode to the next one, and the smallest neighborhood takes a constant proportion beta in each direction. Okay? And effectively, we are counting the number of observations that fall in this interval compared to the number of observations that fall in the larger interval, and we apply a simple Bernoulli Q-sum. Okay? So the previous density is taken by the previous probability is taken from the kernel density estimation, and the post-change probability we defined as that parameter beta, because that would be the maximum value if this is no longer a local minimum. All right, and this is the simple formula for a Bernoulli Q-sum. Okay. Now, a nice approach with this is that it also corrects erroneous splits. So if at some point your model made the split because of the data that it had observed, you can go, if there is no cluster there, you can go back and you can revise that. Okay. So let me just illustrate some experimental results. This is for the case of a static problem, and these are some competing algorithms. This algorithm with thread is a naive or a straightforward implementation of principal divisive clustering. And what you see is that our methods, which are these three, there are different ways of combining steps in this framework, they take a longer time in order to settle in, but once that happens, they exhibit superior performance. This is a case when the number of clusters changes from 20 to 60, and we have a similar behavior. Classroom and the other competing methods perform poorly here. This is the opposite case. We go from 60 to 20 clusters. Again, more or less the same results. And this is the case when we have an abrupt change where all the clusters are reinitialized at discrete time points. And you see that our methods suffer a lot at these breakpoints. So you have to reinitialize the whole hierarchy, and it takes time to build it. But eventually, the performance is improved. This is a histogram of change detection, so when was a change detected, and these are, with the red dotted lines, we have the points at which the distribution was reinitialized. And as you see, these are well identified. Please take into account that some of these changes here refer to fixing the model, so identifying splits that were previously wrong, and we don't need one change to fix the whole model. Okay. Right, and then lastly, one example on real data set. This is from the UCI repository. This is a data set known as forest cover type data. It contains approximately 600,000 observations with 7 clusters. There are 52 features, out of which only 10 are numerical, so we're using them. And what you see here is the proportion of the different clusters, different classes in the data. And you see that there are certainly different phases here. We have, I ran out of time. So you see that there is change, and you see that our algorithm can do something reasonable. Okay? Thank you.
Now we have one or two questions. Right. Comments, if no questions. So my understanding, all your methods you are comparing use some linear classification rules. Am I right?
No. These methods do not use class stream, and HP stream do not use a linear threshold. The methods, the divisive clustering methods use, yes. So all the methods based on our framework use hyperplanes to split the data.
Right, interesting. So they use non-linear classification rules and still perform quite badly. I mean, compared to your methods. Quite interesting. Methods use linear classification rules.
That really depends on the properties of the classes. So if your classes are in very high dimensional spaces, the use of nonlinear methods, at least to my knowledge, has not really helped a lot. There is a lot of research in clustering concerning clusters of arbitrary shapes, so you could have lines or spirals and so on. But such phenomena don't tend to appear in very high dimensional space.
Let's thank you again, Alex.
Thank you.